Today we want to introduce the idea of a second order partial derivative. Now, this is ultimately a second order derivative, so the stuff that goes along with second derivatives that we know about from before, that's still going to be in play. It's going to be a little more complicated because there's going to be more of them, but the thinking is still going to be the same. We take the second derivative by finding the derivative of the derivative. So let's remind ourselves of where we're at. We know that a function of two variables will have two first partial derivatives because we can have rates of change in those two variable directions, the x direction and the y direction. What we want to notice here is that a function of two variables, the two first partial derivatives are also functions of two variables, and so they also have two partial derivatives. So these will be our second partial derivatives. So the notation for this is going to be similar to the notation that we used before. Once again, we can't have prime notation because prime is not specific enough to each of our variables. So we make them a subscript and we put an x for the partial with respect to x, and then we put a y for the partial with respect to y, rather than just prime, because the prime is not specific enough. So we're going to take the derivative of fx with respect to x, and we're just going to tack on another x. Just like a double prime, but two x's. So the partial with respect to x, then again the partial with respect to x. Leibniz notation works much the same way as it does with second derivatives, second order ordinary derivatives. We take the second derivative with respect to z, second derivative of z with respect to x. It's really kind of like a dx being squared, but our notation dictates that we only put it on the x, and we understand that the dx is being squared. Kind of. I didn't say it was a perfect explanation. All you nerds in the comments on YouTube, don't at me. Trick's on you. I turn comments off on YouTube. So if we want to take the partial of z with respect to x and then take the partial with respect to y, the numerator will look the same, dz dx, but the denominator will have two different variables. So we're going to have a dx and a dy. So we just have dx and dy. So we're just modifying our double prime notation to indicate the variables that we use. Now we just put them in order. This is the partial derivative first with respect to x, then with respect to y. This is the partial derivative with respect to x, and then with respect to x. Prime is not specific enough. We've got multiple variables running around, so we need to modify our notation. The same thing happens over in our functions derivatives with respect to y. Our second derivative of y with respect to x will look similar. We like to write the order that the derivatives came in the denominator. So in the first one I wrote with fxy, I wrote second partial of z with respect to x and with respect to y. And then over here for yx, I wrote a denominator of dy dx. And then finally, we can find the partial of y with respect to y. So that'll be the second derivative of z with respect to y twice. And I'll just write two y's. There's my first derivative with respect to y. There's my second derivative with respect to y. So we have 4 second partial derivatives. If we went to third partial derivatives, there will be 8 of them for a function of 2 variables and so on. If we started with a function of 3 variables, there would be 3 first partial derivatives. And so there will be 3 for each of those 3, so 9 second partial derivatives. So each derivative of a function of n variables will have n first partial derivatives, and each of those first partial derivatives are also functions of n variables. So it's going to go up by it's going to go up exponentially. Let's look at an example. Let's suppose we have a function 3x squared y plus 5x sine of y squared. Let's find the 4 second partial derivatives of this function. See, good for a sleepy Friday, just like some mechanical stuff to grind through. Simple concepts like, good, mechanics, I already know. So let's find f. First, we need the first partial derivative. So fx So I'm going to take the derivative with respect to x. So that means anything with a y in it is constant. And it looks like I made it easy on myself. I separated out the x's and y's into nice factors. So derivative of 3x squared is 6x. Y is a constant. Here I have 5x times the sine of y squared. Sine of y squared is constant, just like 5. So I'll have 5x to the 0 sine of y squared. In the partial with respect to y category, fy. We take the partial with respect to y. Now x is going to be a constant. So in this first term, 3x squared, that's a constant factor. The derivative of y to the first is 1. So I get 3x squared. Over here, 5x is a constant factor. So it just gets carried along. The derivative of sine of y squared is cosine of y squared. I didn't plan that ahead. Derivative of sine of y squared is cosine of y squared times the derivative of y squared, which is 2y. So we'll clean this up a little bit. I can multiply 5 and the 2, the 10, and I'll put my monomial in front. So xy cosine of y squared. All we have to do is keep going. Now notice that when we take some derivatives, some additional rules are going to show up, some additional things we're going to have to think about have shown up. So now I'm going to go fxx and fxy. So for fxx, the derivative of 6xy with respect to x, the derivative of x to the first is going to be 1. So I'm just going to get 6y from that term. Now in the second term, 5 sine y squared, there's no x in that term. So that term is constant. So 0 for that term in the second partial derivative. For the second partial with respect to x, then with respect to y, now I don't have any constant terms. The derivative of y is 1, so the derivative of 6xy is going to be 6x. Then the derivative of 5 sine y squared is going to be 5 cosine of y squared times the derivative of y squared, which is 2y. If we clean this up a little bit, we'll get 6x plus 10y cosine of y squared. Nothing fancy going on, just some mechanics, and it's working just like we think it would. It would be weird to call these things derivatives and then have something different happen. That would be weird. Like all algebra. Algebra is just arithmetic. The reason algebra is the way it is because that's what the numbers, how the numbers work. Let's go over to Fy and find the second partial derivatives. First, let's find the second derivative with respect to y again, so Fyy. So in the partial with respect to y, the 3x squared is constant. There's no y in it, so that's a constant term. So the derivative of the 3x squared is 0. Over in the other term, I've got, so this one goes to 0. I've got 10xy times cosine of y squared. So now, because I had to use the chain rule in the first partial with respect to y, I'm going to have to use the product rule in the second partial with respect to y. So notice that this one goes to 0. But this term is going to require a product rule. Math is a reading exercise. We're writing things in code, and so we have to learn how to decode that. It's just shorthand, and we're learning shorthand. So I'm going to break it up into the two factors I'm going to break up into are 10xy and cosine of y squared. So from a product rule standpoint, the first is going to be, I'm going to read as 10xy, and the second is going to be cosine y squared. So I need the derivative of the first times the second plus the first times the derivative of the second. This is all going to be with respect to y. So the derivative of the first, the derivative of 10xy with respect to y is 10x times the second plus the first times the derivative of the second. The derivative of cosine of y squared is negative sine of y squared times 2y. The chain rule is always in effect. We can clean this up a little bit. So I have 10x cosine of y squared minus 20xy squared sine of y squared. Well, it looks like I'm saying these things are all equal. Next, let's find the partial with respect to y with respect to x, the second partial yx. So now the read on fy, the 3x squared, is a function of x. There's no y in it, but we're taking the derivative with respect to x. So the derivative of 3x squared with respect to x is going to be 6x. Now in the second term, the derivative of 10x y cosine of y squared, we're taking the partial with respect to x. So the y of the 10, y, and cosine y squared, that's all a constant factor. That's all just constant factors. The derivative of x with respect to x is 1. So we're left with 10y cosine of y squared. Questions? Just mechanics. I wonder if there's like the equivalent of like an injury from doing math without like warming up, or does this count as a warm up? Like if you're gonna exercise or something like that, you should like run in place. I don't know, move around a little bit just to kind of get moving before you start lifting up heavy objects. I don't know if this counts as lifting up heavy objects, but here's what we want to notice. Notice that our fxy and our fyx are both 6x plus 10y cosine of y squared. We ended up with the same thing. Now, it would be weird if I randomly constructed this to make this happen. So the question comes up, are these two always going to be equal? Because this will cut our workload by a quarter. Instead of finding 4 things, we really only have to find 3 things. So the answer is yes, enough. The answer is yes, enough times that we don't have to worry about it. We only have to find 3. Almost always, our second mixed partials will be equal. Almost always, second mixed partials are equal. It's possible to make a function where the second mixed partials are not equal. I would have to do work to make that happen. So that puts it in the almost always category. For comparison, if we have a generic quadratic polynomial, it is almost always not factorable over the integers or even over the rational numbers. Ax squared plus bx plus c is almost always prime over the rational numbers because we have to do work to give you factorable polynomials. It requires work on my part to give you a factorable polynomial. Not a lot of work, because I know very many factorable polynomials. I can make them kind of on the spot. But in general, almost always, they're prime. If we start writing down random quadratic polynomials, they will be prime. So when I say something like almost always, that means it's just easier to make this happen than it is to make it not happen. Yes. Yeah, anytime if I'm giving you something on a test, I'm not going to put that much work into making a test. If the problem stops working out and you're like, oh, why is this problem not working out? Then you take the thing that you figured always happens and say, well, does this happen in this particular problem? So I don't usually want to do that. Not like on a test. I mean, if you're all sitting here doing problems, I don't want to give you like super stressful problems. I just want to do all trick questions. Any questions? Mixed second partials are going to be equal whatever it counts. If that's going to be a thing, that's going to be the thing on the problem that you're working on. How's everybody okay? We look so sad today. Oh, I was hoping that we would have 4 second partials to find all the time, but now most of the time we only have to find 3. Oh, I'm so sad. So this raises the natural question: what do we use second partial derivatives for? So to that end, let's think about what we use second derivatives for. So let's first remind ourselves what we use ordinary second derivatives for. Let's first remind ourselves of what we use ordinary second derivatives for. Ordinary differentiates from partial. We have partial derivatives and we have ordinary derivatives. later on in your mathematical future, you're going to take a class called ordinary differential equations. The ordinary refers to the kinds of derivatives that you're going to be encountering. The other differential equations class you're going to take is partial differential equation, in which case it's an equation involving partial derivatives. We're not clever with the naming. Don't look for some kind of secret message in the naming. Trying to be what it is on the tin. What do we use ordinary second derivatives for? One of the things that we did with the ordinary second derivatives was determine the concavity at a point and find inflection points. So the concavity was when we looked at second derivative positive or the second derivative is negative. Inflection points where f double prime changes sign. We start finding inflection points by solving f double prime equals 0, but that doesn't mean that we're going to have an inflection point. It's about changing sign. That's more than just f double prime equals 0. Inflection points happen when the second derivative is changing sign. That indicates that the function is changing concavity. We have better language around the first derivative, because when the first derivative is equal to 0, then we call it a critical point. And a critical point could be a local maximum, a local minimum, or neither a local maximum nor a minimum. So one of the things that we can use the second derivative for is concavity and inflection points. Another way that we used the second derivative was to classify critical points. The critical points happen when the first derivative is equal to 0 or the first derivative is undefined. Then we can look at the second derivative. In the case where the first derivative is equal to 0, we can look at the second derivative and check the concavity. So the critical points happen when the first derivative is equal to 0 or the first derivative is undefined. We check the concavity of each critical point. If we see that the function is concave up, then we say it's a local maximum. See the function is concave down, it's a local minimum. Oh, I had that backwards. I wrote that backwards, not for lack of attention, but for adherence to tradition. I write it backwards the first time, every single time. If the function is, the second derivative is positive, then our function is concave up. And so we have a local minimum. If our second derivative is negative, then the function is concave down at the critical point. If the function is concave down at a critical point, that means we must have a local maximum. This is what we do when we see a critical point. because the first derivative is equal to 0. So we can use the second derivative to classify critical points. Note that we did leave off a case when we're classifying critical points. If the second derivative is equal to 0, then it just we don't know. So extra info. So if we're doing this analysis and the first derivative is 0 and we put in the second derivative and we get 0, we have to do something else. We don't know from this information. This information does not tell us things. We have to do something else. You don't just get to say, don't know. Well, actually you do. You just don't get to get any points for that. So that's another thing that we use a second derivative for. We use it to classify critical points. One that I usually forget to mention, one that I forget to mention every other semester, is that we also use this for the quadratic term in a Taylor polynomial. I remember to mention this one every other term because every other term, in addition to Calc 3, I also have a Calc 1 class, and we usually are, at this time, are talking about tangent lines. And if we're talking about tangent lines, I usually can't help it and start talking about Taylor polynomials. So in our second degree term in the Taylor polynomial, the second derivative shows up. What we want to point out here is that the first degree Taylor polynomial is the tangent line. So raise the question, what will we do with partial second derivatives? What will we do with second partial derivatives? I still don't really have a good feel for which one sounds better. Second partial derivatives or partial second derivatives? Because when I use ordinary, I want to say ordinary second derivative. But when I say partial second derivative, that sounds weird. But when I say second partial derivative, that sounds better. But second ordinary derivative sounds weird. English is stupid, and it's kind of a pain in the ass. So What are we going to do with our second partial derivatives? Unsurprisingly, the same stuff. With the second partial derivatives, we're going to do the same stuff. We're going to think about what concavity and inflection would be on a surface. We're going to use it to classify critical points, to optimize some functions. That optimization will look the same as it did back in Calc 1. Take the first derivative, set it equal to 0, and solve, and then analyze using the second derivative what's going on at critical points. The same thing happens if we have a function of two variables, but there happen to be two first partial derivatives. So we're just going to make both of them equal to 0. I want to look for the points where the function is flat in the x direction and flat in the y direction. Then use second derivatives to decide if we are at a local maximum, a local minimum, or neither a local maximum or a local minimum because we're looking at a Pringle. And we're going to use the second derivatives to determine that the same way we did before. When we start building Taylor polynomials for functions of two variables, which we have already done, I'm going to have second partial show up in my quadratic terms. Any questions? Is everybody okay? I told you that Calc 3 was the easy one because we already know all of the calculus stuff. We'll do the same stuff. Just Calc 3 is the easy one. Question? So this is the other reason that I want to do this. I like this topic to land on a Friday. Because we've just had a very broad question come up. What do we do with second partial derivatives? It's the same as the stuff that we did with ordinary second derivatives. That's weird. It's the same stuff, but we have to think about how we're going to modify the old stuff to fit with our new thing. How do we upgrade from ordinary second derivative to our 4, but really 3 second partial derivatives? What is that going to look like? We already know one of them. We already know one because we found the equation for a line tangent to a surface at a given point. And that's just the tangent plane. And that's corresponding to the tangent line. So we know what that looks like. So we know what the first degree Taylor polynomial approximating a function of two variables will look like. But now we have 4, but really 3 second partial derivatives. What's that going to mean for what shows up over here for our quadratic terms? What's it going to look like when we're trying to optimize a function, look for local maximum, local minimum, when we have a function of two variables? Take the first derivative, set it equal to 0, but there are 2 first derivatives. Plug in the second derivative and check the sign, but there are 4 second derivatives. We're going to have to think about how our old thinking is going to have to get updated. Any questions? Comment? Right now, it's like, oh, so the homework is just to think about this stuff. I'm like, oh yeah. So you're saying no homework over the weekend? Like, oh no, the homework is to think about this stuff. And they're like, well, yeah, but there's nothing that we have to write down and hand you or type on the computer, right? I'm like, oh, nah. They're like, oh, there's no homework this weekend. But secretly, there is homework this weekend. Because by not asking you to do any problems, it's going to be running around in your subconscious. I'm giving you subconscious homework. You only think that you're not doing work in Calc 3. Well, haha, got you, suckers. This will be running around in your subconscious. All right. That's going to do it for today. That's going to do it for this week. Everybody have a good weekend trying to not think about Calc 3, but secretly thinking about Calc 3. That's going to do it for this week. I will see y'all on Monday. Everybody have a good weekend, and thanks for playing.